Hi everyone. Today was going to be a short video, but since I've already filmed part of it, it's basically a preamble, an instructional section of Ohm's law and power, wattage and all that. That already takes 18 minutes. So if you want to skip that and get right to the construction of stuff, at the end of this, just jump ahead another 18 minutes and you can start seeing how I'm actually building this new to me load tester, load bank for testing generators. And there's some caveats with it. I'm not telling you how to do it. What I'm doing is bypassing a few safety rules. Dealing with electricity, we're talking about hazardous voltages, hazardous currents. We're talking about heating elements that can do serious damage to you if you let them get too hot. Nonetheless, I feel comfortable in doing this for myself to test two generators here. I've used part of it in the past in even a more amateurish manner. This build will be a little more towards the professional side, but again, there's no safeties to keep you away from the heating elements. If one of the heating elements actually burns through and exposes the 110 volts to the metal case, you could get seriously injured. So I don't recommend doing it this particular way, but it might give you some ideas if you need to do your own load testing for a generator of some sort. Bear in mind, we're going to switch voltages here and there, which changes the wattage of everything quite a bit. And that's one of the reasons that we're doing what we're doing with extra elements and so forth. So thanks for showing up. And hope you stick around long enough to watch this. Once I get to testing, it may be actually entertaining. We'll see. All right. Thanks, and welcome back to the K1LBG Joe Heck channel. Hi, folks. Just a real quick insert here. If you don't want the lesson in Ohm's law and power generation and items like that, and how wattage, current, voltage, amps, electromotive force, resistance, all that work, you can skip ahead about 18 minutes because my monologue on how those items work takes just about 18 minutes. So, and I won't complain if you decide not to take the lesson today for elementary electrics. Thanks. Let's see how this goes. Some of you may be asking, the ones that stuck around and didn't skip all this, why do I need a load tester for my generator? Can't I just plug stuff in and see if it works? Well, I can do that, but a generator is rated in kilowatts or watts, or kVA, which is kilovolt amperes, which, without going into the details of the electronics, is almost the same as kilowatts. So you may see kVA as a rating, or you may see kilowatts as a rating. I need to know if my generator, the one generator that I'm trying right now, which is 4.5 kilowatts, I believe, or 4,500 watts, a kilo being 1,000, actually can handle that. So to do that, I need to place some kind of load on it, you know, connect the house to it or whatever. But I need to be able to control that and know what kind of load, what size load to use. To do those calculations roughly, I'm going to use an analogy of a water tank. And some people are going to cringe. I understand that. But for many people, they have trouble grasping the concept of electrons flowing and potential of batteries and so forth. So let's take what we're looking at. We're looking at a couple of items. We're looking at potential, which in a house is the voltage coming into the house. That's what's called potential. Even with nothing running, your house still has 110 volts and 220 coming into it. When you start using that potential, that 110 volts, in a hairdryer or a light bulb, now you're using some of that potential in the form of current or amperes, typically known as amps. Voltage, and we're going to get into the equations in a bit, voltage times current is power, and that's how many watts you're using. So how does all that relate to what I'm trying to do? I'm trying to find out if I can load up my generator around 4,000 watts. Potential, I just talked about potential. Potential is what's available, not what's being used. In this scenario, I'm not a good artist. These are water tanks or water reservoirs, and these are houses. We have a tank here, and if you think of this tank as being absolutely full, if you connect a hose from the bottom of the tank to this house, you can feed water to the house. Maybe not very fast. There's not a lot of potential. It's not very high. But because it's lower than these two houses, it will never feed these. This potential will never be enough to push water uphill. This one, however, because it's higher up, has a higher potential. And that can flow down to this guy, flow down to this guy, maybe a little slower. And if he were full, he might be able to feed this a little bit. The difference between this guy and this tank, there's not a lot. That's called potential. Even with nothing hooked up to it, this could be full of water and have the potential for creating a flood even, if it were to burst open. And I believe you'll find that that's stored energy, potential energy. Now, if you hook up a pipe to this and you start drawing water out of it, now it's being actively used. However, if you use a really small hose coming out of here, really tiny hose, and you go to this house, and you also go to this house, this guy may not get anything because he's going to use all the available water because the hose is too small. If you think of a tank, which you don't know how much water is in it, in this case, and you use a small pipe, you're not going to get a lot of flow out of this. Use a bigger pipe and you get a lot more flow. Roughly, the analogy is roughly, whatever this is your potential, which is voltage. And in our houses, we typically have what's called 110/220. Years and years ago, and in certain instances, it used to be actually 125, 250, 120, 240, 115, 230. Most of the country has been standardized now, but you can find areas where the final transformer might be running a little hot, so the voltage is a little higher or lower in that neighborhood. The pipe, which is a restriction or a flow allower, an allowance, the opposite of restriction. The bigger the pipe, the higher the allowance. and the less restriction? Well, in an electrical circuit, we consider that as ohms. I won't say too much about ohms, but that's resistance. And the reason we need to know about that in this instance is we are going to use resistors with very low resistance. So we're going to draw a lot of current. So we need a value which is high in which is low in resistance. And that's where we're headed with that. And I'm not going to say too much about that until we actually get to talking about that. If the tank, however, were very low, it doesn't matter too much how big these pipes are. You're still not going to get a lot out of it. If the tank has its full potential, then the bigger pipe will flow more water, or the higher potential at 110 with a bigger wire, less resistance so the electricity can flow better, the faster it will come out and create more usable power. Power, I didn't talk about power yet. Well, there's a triangle, the magic triangle, some people say. You put a V here, I, R. You might see that sometime, you might never care. This is Ohm's law, and it has to do with your potential, your current flow, and how much resistance you have in your system. Basically, and the reason it's in a triangle is you take any one thing and the leftover is the components of the equation. So current times resistance gives you voltage. Voltage over current equals resistance. And voltage over resistance equals current. I'm going to say sort of live with that because we talked about voltage potential, the size of the pipe, and how much flow we have. The analogy isn't perfect there. Now, if we talk about the size, the height of this, and the size of the pipe, which is, this is the voltage supposedly, and this is the current availability, VI, voltage times current, equals power. And that's the power we're looking at. Power is in watts, as I had said, I think. And I'm trying to draw, using 110 volts only on my system, I'm trying to draw enough current to get my 4,500 watts so that I can fully load down this generator. What's that got to do with resistance? How do I know what size my load needs to be? You know that you hear so much about power. Your hairdresser might be 1,000 watts or 1,100 watts or 1,600 watts. I don't know if you have an electric dryer or an electric hot water heater, you might have gotten close to having to deal with wattage on those. But given this, I know the voltage, it's 110 volts. I know what power I'm trying to reach, but I don't know the current. So how do I get the current? What I have are these big resistors. They may be heating elements out of an oven or from the stove top. They may be the hair dryer. The hair dryer, I already know what the power is because it says it on the side. But let's assume that fell off. How do I determine this? Well, I don't really need to determine current. I can take this derivative of this triangle and substitute for I. So now we have power equals V times V divided by R. So given the resistance of any item, I know my voltage in the house. I can get the power, how many watts that particular resistor will use. Resistance, you say? Well, yes. Another term, I don't know what I want to say what it is. It's an attribute of imperfect material. If you try to put electricity through a piece of plastic, you put 110 volts there and 110 volts here, well, you get no current flow. This is an extremely high resistance because it's an insulator. That's what they call an insulator. Conductor. A conductor, well, we could take a drill bit. It's steel. It's not perfect, but it's pretty close to being perfect. Enough so that if I put 110 volts across this would probably glow hot and trip a circuit breaker. Every item has some sort of resistance. It's somewhat intrinsic when you're running electricity. Light bulbs, a 100-watt light bulb. Well, let's call it a 110-watt light bulb. If it were an old incandescent light bulb, if you had 110 watts at 110 volts, you would be drawing 1 amp. Oh, I'm sorry. Yeah, you'd be drawing 1 amp because 110V times 1 amp is 110 watts. What's the resistance of that bulb? Well, it's 110 because at 1 amp, 1 amp into 110 volts gives us 110 ohms. Ohms is a term used to say how much resistance there is. 500-watt bulb draws five times as much current. And we're working backwards because we have watts. Well, I need to know how to determine how many watts a device will take without using that. So what I am doing in the practical aspect, whoops, and I will show you. This is a heater out of an electric hot water tank. I already know this is 4,500 watts, but it's at 220. So how many watts is that at 110? Well, it's not divided by 2. It's more complicated than that. It's essentially a quarter because we have this V squared nonsense. So when you're having the voltage, you're actually creating 1/4 because 1/2 times 1/2 is 1/4. So I know what the resistance is by looking at that, but it's easier to just measure the resistance across here. And the same goes for this one. This says it's also 4,500 watts at 240 or 208. That's fine. So I don't need to know any of this for these two elements. I know how many watts they are. And they're not enough because if these are 4,500 watts, they're basically 1,000 watts each. 1,100 watts. Well, that's only 2,200 watts. If I'm trying to get up to 4,500 watts, I need something else. And that's where we start looking at what else I have around here. Do I have some stovetop heaters? Do I have some stuff from an oven? Do I have an old electric dryer heat element? Do I have more of these someplace? I'm going to stop here because now we're going to get into the aspects of building. And I know I went through this fairly quick. There's tons of information on power and voltage and resistance and Ohm's law out on the web. But hopefully this gives you a little bit of understanding, because you need to know, if you can't see inside this tank, you really don't know how full it is. So you don't always know all three values: the voltage, the resistance, and the current. So with these two formulas, this one and this one, you can determine your power, your voltage, your resistance, your current. We're lucky here we already know what the power is. The device we're going to use, I don't really know, or I don't trust the power. And I'll explain that when we get to that, which will be in just a second for you, because this is where we're going to stop doing paper stuff and actually go look at the build. This is the basis of my load tester. It is the heating elements from a sauna, Hilo sauna. However, it's not really made for the house. You can't see it very well. Can't see it at all, actually, because it's too fuzzy. But this is a 9 kilowatt, 208 volt, 3-phase unit. And it uses 10 gauge wires with a minimum rating of 90 degrees centigrade. That will come in handy when I actually go to put this together, because that allows it to use, it allows the wires to get a little hot. If you skipped my discussion, 9 kilowatts, 208 volts is really only a couple of kilowatts when you run it down to 110 volts. So what's all this about? Well, you'll see in a second. I'm going to set you up on the tripod here and go through it. So you can see 1, 2, 3 heating elements to make the 9 kilowatts. And of course, I'm not taking a whole bunch of safety covers off just to get the weight down, and they all come out to here. Now, as I had said in the learning section, that each one is 3 kilowatts if it's a 9 kilowatt heater. You have to divide that by 4 to half the voltage. So 4 into 3200, let's say, it's about 800 watts per heating element. That only gives me 2400 watts or so to test my 4500 watt generator. Well, you know, running half load is probably a reasonable thing to do, but I want to be able to get this up to at least the mid 3000 watts. So what I've done is I've actually, and the people that watched my power tutorial before this will recognize this. This is a heating element from a water heater. And strangely enough, this is another heating element from a water heater that puts out the same amount of watts. They're both 4,000 watts at 220, which makes them 1,000 watts at 110. I am going to clamp these like this using insulating material so we don't short anything out unnecessarily. And I'm just going to clamp them down like that and clamp them like that and wire them into my circuit. Now, because there are so many combinations of series and parallel, I can go from testing like 200 watts up to close to 4,000 watts, I believe it is. If I put them all in parallel, we already know that this is 800 watts. Did I say this was 800 watts? Each one is 800. So 3 into 800, 3 into 900 watts, call it. So this looks effectively like 300. I take it back. I'm confusing it here. This is 2400 watts. If I take this guy and put them in parallel with it, that makes it 3400, and another 1000 watts from this is 4400. So I can get close to 4500 putting all these in parallel. If I put them all in series, that will give me like 300 watts effective. Now what does that mean, series and parallel? Well, let's just take these two top items. If I run a wire from here to the top one of here and the bottom of here to the bottom of here, they're in parallel, so I have one set of leads here. And effectively it makes it look like the resistance is half of what's here because these are equal elements. If I put them in series, so I run one wire into here from my generator, the bottom goes to the top here and the bottom comes back to the generator. Now I've doubled the resistance and the wattage goes down to half of that. So instead of 1000 watts, that's only 500 watts. If I put all these guys in series with it, I get down to 200 or 300 watts. So I have to be able to either design a very intricate switch with about 20 settings, or I'm going to just put, I'll call them quick connects. They are what are called Anderson power poles. And for the price that I paid on eBay, I'm pretty sure they're knockoffs. But they're supposed to be good for 30 amps. I don't believe it. At 110 volts, I'm going to be nowhere near 30 amps. But if I were to use this on 220, they might get a little toasty, as would all these. So that's where we are right now. The first part is to take these guys and clamp them in place. So how to do that, they're two different heights. What I'm going to do is put those on there, and this on here, which is for some reason exactly the width I need. I didn't cut them that way. I had them in my scrap pile, and they're within 1/4 inch of the width. So I'm going to put those on there like that, and then just strap from here down, and just hold both sides so that they're in a good spot. Now mind you, this isn't going to be going anywhere. I'll be lucky if I use it once every 5 years. It's only me that's using it. That's not probably the best way to support all this, but it's the way I'm going to do it because I will feel comfortable enough doing it that way. All my leads are all right here, so I know nothing on the other side can get me. I just have to be careful here. And indeed, most of the leads are going to be in insulated connectors, so again, that should make it a lot safer. So let's see how we're going to mount this. All right, first connection. I bent a piece of flat aluminum and bolted it on. Put 3 holes in here for self-tapping screws. I'm going to drive 3 self-tapping screws and then repeat. Rinse and repeat. All right, I'll do that for the other 3 now. All right, so let's take a quick look at where we are. These 2 heaters are mounted. The screws face out this way, like as they should, because here's my 3 leads from the 3 heaters inside and the other 3 leads on the back side. I simply use self-tapping screws, self-drilling screws, whatever, in here. Sandwiched the heating element to get it approximately the same height as the other. Because it's doubled up, I had to use these aluminum blocks. And I clamped it down, so it's going to stay there pretty tight. And this side, because it has a double length element that was folded over, I put blocks in the middle of it so I didn't crush it. So that's it. It's kind of held in by friction, but it's pretty tight. So the next is to wire this all up with the appropriate wiring, and we'll go from there. I'm not going to bother showing you the wiring. It's wiring is wiring. There might be a couple little tricks that I use, but I have to straighten him out. He shouldn't be out like that. But little stuff like that, which is really trivial. Crimping on the Anderson power poles is pretty standard. So hopefully the next time you see this, I will have it all wired up with a proper cord on it. I don't know what I'll use yet. And then get ready to test it out. We'll see if I can make it that far today. Okay, folks. Just a slight change. It turns out that the power poles that I bought off of eBay, they aren't very good. I think they're knockoffs. They don't make good connections. So I scrounged up some that I had. And as a result, I don't have enough connectors to do all the combinations of serial and parallel. However, I do have enough to do one load or parallel 2 or more loads. And it actually, let's see if it shows up enough. So I can do from, just with this setup with the 5 units here, in selecting a single unit or double units, triple, 4, or all 5, I can go from 800 watts. It should focus. It does. 800, 1000. Then there's a jump to 16, then 18, 2000, 400 isn't too bad, then a small jump, 26 and 28. Then there's another good sized jump up to 34, 37, 45. My target with this is to see if it will do, let's say, 3700, only because I need to do at least 2500 without it going crazy. So that's where we are. The next step is to roll the generator back outside, hook it back up, get it running again, and then we can use the load tester. Well, yet another video that's not going to turn out the way I wanted it to. So here we have 4,500 watt generator, RV generator. And I've already taken off the air filter, played around with the governor, plumbed in the gas directly to the carburetor, thought maybe I had a fuel pump problem. It's going to be really noisy. I'll try to back it off because my exhaust pipe keeps twisting and falling over. But I can't get 4,500 watts out of it. I'll try to show you what's going on. Basically, I have an amp probe here, And I don't know why. Well, you can see it goes to 40 amps on this scale. And I should mention, before someone else yells, these Anderson power poles that I have that I'm using on 120 volts are actually low voltage DC connectors. Oh well, that's something that I am aware of. And because I have no ground reference here, it's not as critical. Yes, you can still get yourself electrocuted, but not today. So the first thing I did, and I will probably show it again, and I may mute all this while it's running, but I actually cut a small hole in here so I could really see that I'm at 1800 RPM. This is a 4-pole generator, runs at an 1800 RPM. It makes it for a really long lasting engine. So what I'm going to do is I think I'm going to parallel up these 3 here, which gets me about 2400 watts. I'm going to start with 1, which is 800. Then 2 is 1600. Then 3 is 2400. And I think it's going to fail around there. We'll find out. And we'll go from there. I'm going to give that a shot. I don't run it that long because I don't want everything to get really super hot on me. But here goes. So let's see. What can I do? Okay, I will just show you all this. I can do this all sort of one-handed. Well, we have a new problem. The engine should be pretty warm, and the choke isn't opening. So we'll have to see if it stays open. And it does not, which means Alright, so you can see it starts galloping. when I put I put the three lower ones on, which should have given me, well, I'll look at it, but that should have been around 2,500 watts. Those are the three lower ones that I've got here. Then when I added the extra 1,000 to get me up to 3,500, it didn't like that at all. I could jump back a little and try a little less, but I don't think I want to. It's getting it's getting to be winter out here, even though we don't have snow here in eastern Massachusetts. But I'm at the point that I seriously need to look at this carburetor, look at carb adjustments, look at choke adjustments, before I can go any further with this engine. But you can see, instead of trying to power up my lights on that light tower trailer, how useful this is. It's a nice resistive element, and you can see that there really is a problem with this engine, and that means the diesel engine that I was trying to use it on earlier definitely has a problem. So I think we're going to call it quits right here. I was swapping in each of these lower units. These are about 800 watts each, and then I put 1,000 on. So I did quite a jump. I could have done two of the top ones. Well, maybe I'll try that. I'll do two of the top ones, and then that's 2,000 watts, about 2,200, and then put one of the 800s on. Let's see what happens there. I guess I can do one more test here. Let me pause you. Okay, so I hooked up the top two, and I'm going to try to start it under load, which may be a mistake, but we'll see. Wow, one more time. I had decided to do the test, one more test. So I hooked up the top two, which are basically a bigger load than the three bottom ones. These are around 1,000 or 1,100 watts. These are only around 800. So what I had done is I hooked up the two top ones, and that seemed to work really pretty well. So let's call that 2,000 watts. And then when I hooked up one of the bottom ones to get me around 2,800. Actually, this, if I look at these say they're 4,500. So call it 1,100. So 2,200. When I hooked up one of the bottoms, which is around 800, gets me up to 3,000 watts. It failed. It started galloping just like before. Only before it was around 3,400 watts, 3,500, based on my configuration. So this is nowhere near the 4,500 watts this is supposed to be able to put out. Clearly, I either have bad gas, a bad carburetor, bad adjustments, bad fuel pump. But I think I'm done for the year. This was really more about testing this thing, this homemade load bank, and that worked out pretty well. I was able to do it to figure out just where this thing started dying, and reasonably easy just by moving some jumpers. A little more difficult because I was trying to hold the camera while I was setting up these jumpers. I think I already mentioned in a previous few minutes, these are low voltage DC connectors, Anderson power poles. For 110 volts, they're okay for what I'm doing here. I don't know if I'm going to trust them at 220. Might be a little more careful. Certainly connect them and disconnect them with them de-energized, which again I didn't do here. So this is not a how-to. This is what I did. Might give you some ideas. Here I have a couple of hot water tank heaters on top, along with this old sauna. I don't know, maybe an oven element would be good. I don't know how many watts an oven element is. But it showed me that I've got things to do on this. Starting with old fuel, which I don't think so. Bad fuel pump, which I bypassed. The choke hangs up, which it shouldn't. Idle and high-speed adjustment. Idle adjustment shouldn't make any difference on a generator. The high-speed adjustment doesn't seem to make a difference. I've adjusted the governor. It shouldn't be galloping. So I'm done. I can't use this generator for what I wanted to. At least not until I get it fixed. So that's where we are, folks. I built this. I showed you what I did to test with it. I know it looks like a bunch of spaghetti here, but trust me, they all have a purpose. There's 5 black and 5 red, and they equate to the 5 elements. I could actually hook a red to a black and put some in series. I didn't want to do that. I was just trying to get a rough guesstimate if this was even anywhere near its full potential, and it's only about half. So now to put everything away. I checked, I cut a small hole here to use my mechanical tack to make sure I'm at 1800. So the governor seems to be about at the right spot, but it's too sensitive, not sensitive enough. I don't know which way to go with it. But first I think it's time to rebuild the carb or put a new good carb on. And that's where I am. It's getting cold out here. Middle of November. I'm not going to work outside anymore this winter, I don't think, unless I have to, plowing snow. So I'm going to pack all this stuff up. I hope you found this interesting, laughable, unique. It certainly is a little more permanent than what I had before. I suspect if I use this to its full potential on 220, I can probably get about 12 kilowatts out of it. But I'm not there yet. If I can get it to work on this little one, that'll be fine. Anything over about 6 kilowatts means the generator's doing what it should, I think. Well, if you like it, fine. If you don't like it, fine. You can either do a thumbs up, thumbs down, comment, share, subscribe, say hello. All I can say is I hope someone finds this interesting and gives them some ideas for what they can do. All right, guys, you have a good afternoon, evening, or morning whenever you're watching this, and we'll see you on the next video.